Today we will talk about a topic is permanent magnet, and this is our team member. This topic is very popular and very hot recently. And online, first we can introduce the samarian cobalt magnet and neon magnet. And third, we can mention about how to do toward stronger magnet. And fourth, we will highlight new permanent magnet, and it is iron nitride. And finally, we will discuss application model. First, it is a nickel magnet. It developed about 30 years ago, and it composed of aluminum, nickel, cobalt, and iron alone. And this is a binary phase diagram. And first, this is iron cobalt, and it's alpha-1 phase, and a basic structure has magnetic property. And the other is the nickel aluminum. It is alpha-2 phase and cubic structure and non-magnetic. And one of the most important is in the middle of the phase diagram is the alpha-1 and alpha-2 coexist. And the size of the region is determined by appropriate heat treatment. And when I apply the external field during the spinel decomposition cooling from 1200 degrees Celsius, and we can find iron cobalt particle will be precipitated and are aligned parallel to the field in nickel aluminum matrix. And the phase segregation can be improved by a nearly 600 degrees Celsius. And from this picture we can see it's very obviously clear. And next part, it is the samarian cobalt magnet. And the principle is located at the cobalt-rich phase, just the first circle, and it can classify into two parts. First is samarian cobalt 5. It is FCP structure, and the samarian atom is surrounded by the FCP structure of cobalt atom. And the other is samarian to cobalt 17, and this structure will be derived from the samarian cobalt 5 FCP structure. Because why? We like 1/3 samarian atom is replaced by the gunfield pairs of cobalt atom. And of course, this replacement will destroy the anisotropic energy of the cobalt atom. But samarian and cobalt magnets, and there is anisotropic energy derived from 60% of samarian atom and 40% of cobalt atom. And the replacement leads to the two structure of the samarian to cobalt 17 is compound. First, the stacking order is ABC, ABC, and the other one is AB, AB ordering in the FCP structure. Okay. Next one. This is the relationship between the coexivity and microstructure. And there are three hysteresis loops here. And first one is the nucleation type dominant to coexivity mechanism. And we always hope the magnetic powder is smaller and the number of defects is fewer. So the reversal domain of nucleation sites is also fewer too. So we can see the microstructure here. And the circle is represented the defect, and it is also a nucleation site. And we can see the bending shape as just like the river, and it means the reversal domain size, and it is speed up and speed down here. And the second is a pinion type dominant, and we can see the inclusion is precipitated in the matrix, and it can hinder the domain wall to move. So it can achieve a higher coexivity. And the third is distribution of pinion center, and it's just like the first one. And except for their pin center is much more than depletion type. So the best and the highest coercivity is the number one, the depletion type, because we can see the hysteresis loop is largest here. And I can jump the conclusion. The ferrocobalt magnet has high energy product coercivity and oxidation resistance. Because of high price, most of them is replaced by new magnets. But higher temperature coefficient is a characteristic of the ferrocobalt magnet and is unreplaceable. And next part, I will give my partner to introduce about the new magnet. Thank you.
Okay, in this part, I'm going to introduce about the different system, near system. And before start this topic, maybe you will question about why we should use another real Earth system. The key is performance. You can see a left figure. The near system has the better magnetic property, such as the coercivity. And the left figure shows the evolution of hard magnetic materials. Those magnets have some magnetic field, but have a different value. We can find a near system has the smallest value. It's very useful and powerful for the motor application. And about this application, we have a talk by following speaker. So in general, the near system is still the major solution now. Okay, and now next page, I'm going to talk about the detail of the near system. The composition of the near system is shown here. Depending on different process, there are two kinds of near magnet. One is a singly near magnet, and the other is a bundling near magnet. And you can find this table. The different process will make different magnetic properties. And the near magnet is not a single phase magnet. For example, the singly near magnet has a three phase. So I'm going to talk about the three phase. The first main phase is shown here. This phase is also called the T1 phase or tetragonal matrix phase. And only this phase has a magnetic property. The second main phase is the neodymium and rich phase. This phase is also called the T3 phase. And this phase is easy to find along the grain boundary. You can find the index picture. The A point is the T3 phase, and the B point is the grain boundary. The T3 phase grows along the grain boundary. The minor phase is the composition of a minor phase is shown here, which is called the T2 phase. It's a forward-rich phase. This phase is difficult to distinguish from the matrix phase. So we need to use the diffraction spectrum and the phase diagram to find it. Here shows the diffraction spectrum and the phase diagram. We can find this peak come from the T3 phase, and this peak come from the T2 phase. So this figure can prove the near system has a T2 phase. And the left figure shows a field diagram. We can find here is a T2 phase. So the near system is listed the T2 phase. Okay. The near system has a three phase. Unfortunately, only T1 phase has a magnetic property in the room temperature. So we need to talk about the T1 phase. This is the T1 phase structure. It's a tetragonal structure. So it is also called the tetragonal matrix structure, tetragonal matrix phase. And this table shows the magnetic property about the T1 phase. And those magnetic property, we should note the Curie temperature. We can find the near system has a lower Curie temperature. It's a big problem to limit its application. To overcome this problem, element addition is a good solution. In fact, this way is widely used to improve the magnetic property. For example, Cooper addition will increase the Curie temperature. You can find this figure and this table. If you added more Cooper in your near system, your Curie temperature will also increase. Another example is dispersion addition. You can find the dispersion addition will increase the corrosivity. In fact, element addition is just one kind of a way to improve the magnetic property. So next part, my partner will talk about another way to improve magnetic properties.